We'll hear from Jamie Sikora more about quantum coin flipping.
Thank you. And I'd like to thank the organizers for inviting me. So welcome everyone to part 3 of 4 of coin flipping morning. So I'm going to be talking about some work with Ashwiniak and Levin Tinchel at the University of Waterloo, and some quantum and classical coin flipping protocols based on big commitment and their point games. Okay? So this is a bit of a mouthful. Basically, we're going to have fun with crypto SDPs. Okay? So we saw some SDPs this morning, and we're going to have some more fun. Okay, so we heard this morning from Udanis about weak coin flipping. Okay? So just a quick recap. We have an Alice and Bob. They're going to communicate with some communication protocol, and they're going to output some general uniformly random bit generated by the protocol. In weak coin flipping, we adopt this notion of security, where Alice wants outcome 0 and Bob wants outcome 1. So you can think of a notion of a winner and a loser. And as we've seen this morning, we have good weak coin flipping protocols. We can make these both arbitrarily close to 1/2. Okay? And this talk is going to be a little bit more concerned about strong coin flipping. So a strong coin flipping protocol is still a coin flipping protocol, but we have a stronger notion of security in this sense. Namely, we want to bound all 4 of the cheating probabilities. So Alice could cheat towards 0, but she may also want to cheat towards 1. Bob could want 0, or he could also want 1. Okay? So it's the same kind of protocol, just a different notion of security. And we know optimal bounds for these as well. So Kitaev's lower bound shows that the product of the 2 cheating probabilities is at least 1/2. These quantities are at least 1/2, so the trivial lower bound would be 1/4. So this is a nice constant lower bound. This was also shown by Kotowski and Watrous in 2007, using a formalism of quantum strategies. And I guess we'll hear more after this talk, another proof. So notice this doesn't apply to weak coin flipping, because here they want the same outcome. Okay? And we can show that this is tight, or arbitrarily tight, shown by Shayun Karanidis. We can have protocols that make all 4 of these cheating probabilities arbitrarily close to 1 over √2. Notice this guarantees at least 1 over √2. So there's this constant lower bound. But these optimal protocols are based on weak coin flipping. So we understand these optimal protocols for strong coin flipping about as much as we understand them for weak coin flipping. So what I'll be talking about in this talk is looking at a simple class of strong coin flipping protocols, or just coin flipping protocols. And we'll look at their security, and they'll be more simple, and we'll be focused on how to prove their security. Okay. So first, I want to show you a bad coin flipping protocol, and then we'll see how to fix it. So Alice is going to choose A uniformly at random and send it over to Bob. Bob is going to choose B uniformly at random and send it to Alice. And they're going to output the XOR of the 2 bits. Okay? So we see they agree on the same bit, and it's uniformly random. But the problem is that Bob can cheat arbitrarily. So he doesn't have to choose B before seeing A. He can choose it after. So he can basically choose the outcome of the protocol. And Alice cannot cheat at all. Okay? So this is a bad protocol. And we want to look at how to fix this. And the problem was that Alice was sending too much information too fast, and Bob was sending all of his information later in the protocol. So we want a way to kind of balance these two, this transfer of information. Okay? So we're going to do this with quantum states. So Alice is going to choose A in superposition. Okay? So Alice is still going to have an A, and Bob's still going to have a B. But we're going to have them sending information to each other in some quantum way. So controlled on A, she's going to create this state here. Okay? So X is an n-bit string. And it's going to be weighted in some way according to a probability vector alpha A. So her choice of states, the parameters defining them is alpha 0 and alpha 1. And for different choices of alpha, we'll see that we'll be slowly leaking information about A to Bob at different rates for different values of alpha. So altogether, she's going to create this state down here. So she has 2 copies of A, one for herself and one for Bob. And then she has some way to send some messages before she reveals A. And Bob is going to do the same thing. Bob is going to create B in superposition and, according to 2 probability vectors, create some kind of state to reveal his information about B. So we can assume he just creates this big state down here. So the last thing I'll say is that this entire protocol is defined by 4 probability vectors: alpha 0, alpha 1, beta 0, and beta 1. And the goal here is we want to choose these 4 probability vectors in a way to minimize the forward-cheating probabilities. Okay? Moreover, find a way to study and calculate what these probabilities are when you are given a protocol. Okay? Are there any questions about the definition of the protocol?
Yeah, so I don't know how messages are exchanged. It seems like you defined initial states.
So yeah.
Sorry.
So this is the communication of the protocol. So that was the setup. And they're just going to send information like this. So this is, so we have 3 messages at the beginning. So X is a 3-bit string. And Alice is going to send X1 over to Bob. And Bob is going to send Y1. So they've created the states, and now they're just switching registers. Alice is going to send X2, Y2, X3, Y3. And now, at this point, they're ready to finally reveal what the bits are to each other. So Alice will say, OK, well, we're at the end of the protocol. Here's my copy of A, so you can calculate the outcome. And here's a copy of X, which you can use for cheat detection, which I'll say more about in a second. And Bob says, OK, that's great. Thanks for A. I'll give you my copy of B and Y for cheat detection. And what they're going to do now is just measure and find out the outcome and whether they should accept it. So the outcome of the protocol is going to be the XOR of A and B. So Alice can perform some measurement to see whether A and B are equal. But there's also some kind of cheat detection step. If Alice knows what B is, then this state should collapse into this state down here. Okay? So she can perform a measurement to see if it's in this state. And if she detects that it's not in this state, then she'll abort the protocol. Okay? And aborting is bad. So whenever it's aborted, there is no outcome. And so Bob wants to force some outcome conditioned on not aborting.
I'm a bit confused. Where do you get 4 Ys from? So,
sorry, Y is just Y1, Y2, Y3. It's another copy.
ah,
It's just a copy.
it's
That's
a
all.
3-bit state.
Yeah, 3-qubit. And also, Bob can also measure the outcome of the protocol. And since these were in superposition and everything was nice, he gets the same outcome of the protocol. And he can also have some kind of cheat detection to check Alice. So this is the protocol, and we want to calculate its security. We want to look at some SDPs, some point games, and have some fun. So here's an SDP. So we've seen some this morning, and this is basically an SDP the way Kitaev would formalize it. It's a little bit simpler since we have a specific protocol. We can exploit some of its structure. So basically, this right here encodes the betas, and this is the state Bob has at the beginning of the protocol. And what this SDP captures is the state. You can think of the full state of the protocol after each of Alice's messages. But the thing is, Alice, who's trying to force an outcome of 0 here, she can only change the global state of the protocol by a certain amount because she only has possession of part of the state. But she can change it in any way she wants for her private qubits. So we have these variables are the quantum states under Bob's control. And we have a constraint for each round of interaction with Alice. So she can change this quantum state a little bit at a time. And at the end, Bob has some projection, which he's going to apply. And this is going to be the probability that he accepts an outcome of 0. So this is what he wants to maximize. This is what Alice wants to maximize for an outcome of 0. And this is an exact characterization of the cheating.
So is that the same SDP we had in Uranus's talk?
It's similar, except we don't have any unitaries. So this structure of this protocol is very simple. You create states, and you just switch registers. So there's no unitaries in between messages. And we've gotten rid of the message space.
So, I mean,
But it's the exact same idea.
It's a special case.
right, okay.
It's a special case, yeah. Okay, so let's slide this up and have some fun. What we can do is we can write this down in a very simple structure. Okay? So we have here a bunch of large matrices, plus semidefinite matrices. And we can rewrite this in a way such that we're optimizing over a polytope. Okay? And these polytopes are nice. So we have a bunch of non-negative vectors. And these vectors are much smaller than the size of these matrices. So complexity-wise, this is a much simpler problem. Okay? In terms of actually solving these on a computer, this guy up here, for a small instance, could take up to 3 minutes to solve. And this guy takes about 0.08 seconds. So even computationally, you start seeing that this is a much simpler optimization problem.
Sorry, can you quantify big and much smaller? You
So
said they're very big matrices, and then you said they're very much smaller vectors.
So up here, the size of all the sigma i's are the same size, and it's Bob's entire Hilbert space, his whole quantum computer. And over here, this is just the size of his first message received from Alice. And this is the size of the first 3 messages, and so on.
As quantum states.
So
As quantum matrices.
these are quantum states, yeah, and these are just the diagonals of part of them. So if we have sigma 1 is some really big matrix, then S1 is this big. So this would be S1, S2, so forth, and Sn will be the whole thing.
So it's kind of quadratic.
Yeah, in some sense, yeah. So it's much simpler. And up here, we don't have a polytope. So we have a lot more structure, and solving these things or getting an understanding is kind of messy. But it's still a nice problem. I didn't want to put a sad face. It's still a really nice problem. But this guy's here, he's a lot happier because we have a polytope and a much simpler thing, and we can do some stuff with it.
I mean, what you're saying, sorry, you had an SDP upstairs, and now you have an LP, right?
And almost LP. So this is a feasible region of a linear program, but we still have some concave function up here. So this is the classical fidelity of 2 probability vectors. So we're maximizing concave function, so it's a nice convex optimization problem. But it's much simpler. In fact, you can write this fidelity function as a very small SDP. We can characterize it as a SDP constraint. So I'll still consider this an SDP, but it's a very simplified one. And we can do this for the other forcing probabilities. This is just for Alice forcing 0, but we can do it for forcing 1 and Bob forcing 0, 1 as well. Okay, so let's take a step back and see what we've done and where we want to go. We've defined a quantum protocol, and we have Bob's and Alice's SDPs, so we can calculate their cheating. What we can do once we have these SDPs, or the simplified ones, we can take their duals, and we're going to mash them together to create some point games. So the way I think of it, protocols are cheating strategies, and point games kind of have this duality nature to them, and this is through semi-definite programming. Okay, so here's a point game idea. We've seen this morning, but it's worth seeing a few times. We start with 2 points, one at 1, 0, and 0, 1. And we're going to associate to each point a probability. And then we're going to start moving these points around in some magical yet undefined way, such that we end up with a single point and accumulate all the probability into a single point. And as we heard this morning, so I'll say the way to move them around in a second, but basically the eigenvalues of the dual variables are the points that you're sliding around. Okay? And the idea is to strip away this messy basis information to find out how to slide the points around. Okay? Fortunately for us, we've reduced the problem so much that basis information is negligible. There's basically no basis information to worry about, so our point games will end up being quite simple. So okay, I'll show you what the point games look like, but here's a bit of notation. So we're going to be moving points around in the xy plane, the non-negative orthin. And Q here is going to be the associated probability with this point. So here's a couple things we're allowed to do. We have a point, and we're allowed to increase one of the coordinates, either the x coordinate or the y coordinate, and keep the probability. Okay? I just shown it for x, but you can also do this for the y coordinate. And you can point merge. So if you have a bunch of lines, a bunch of points on the same line, you're allowed to combine them in a way such that you accumulate the probability, and the new x coordinate here is just this weighted arithmetic mean. Okay? So there's some nice way to bring them together. So here's a very easy point game. We just have 2 points, 1, 0, and 0, 1, each with probability 1/2. We're going to raise one of the points right here. So now it's horizontally aligned with this other one. And then we can merge, like I said. And now we have 1 point, and we're done. This is the final point of the point game, and it's right here at 1/2, 1. And we can also move this guy to the right, and then merge like this. So we can merge vertically as well. And this is the final point of that point game. Okay. But we're going to need a little bit more mass if we want to do these quantum point games, but not too much more. So we'll need the notion of point splitting. So point splitting, you have a single point, and you want to kind of explode it into several points, either horizontally or vertically. And the way you do this, you have some kind of accumulation probabilities, and they end up being the individual probabilities of the points that are split. And you have to you preserve this kind of weighted harmonic mean down here. So there's a little xi down here, and that ends up being the points over here. Okay? So it looks a little scary, but the pictures are a lot nicer, so don't worry about it. You won't have to memorize this by any means.
Splitting is just the inverse of merging, right? No?
No. If you split, then merge, you'll get some other thing. Conceptually, on a picture, yes. Exploding and bringing it back together, but yeah.
Great.
Life isn't so kind. Okay, so here's Bob's dual. This is the dual for the reduced problem. And what we can do is we can just look at each constraint, and we can see that each one corresponds to one of these point moves. So right here, so VA is a vector, and diag is the diagonal matrix with VA on the diagonal. And this right here, you just take one of the probability vectors, square root each one, and then take the rank 1 plus semi-definite dota product. And if you look at this for a while, you can rewrite this in terms of this harmonic mean kind of thing. So we have the sum of this guy here has to be less than or equal to 1. And that ends up being a point split. And each thing here corresponds to something. So we have a sum here, and this will correspond to a point merge. And these inequalities will induce point races. Okay. And one thing that's nice about the dual, if you're familiar with duality theory, if you're given any satisfying assignment of these constraints here, this value up here will be an upper bound on how much Bob can cheat, since this is a minimization problem. So this is a way of upper bounding how much Bob can cheat towards the outcome 1.
Jay?
Yep.
So is this because of your special kind of protocols, or in general you can...
This only holds for a special kind.
Okay.
Yes.
So
yes,
I
yes.
give you the dual, you cannot tell me here is my split and here is my merge in general. Do you
No.
have an intuition? Okay.
No, no. So you might have some...
Because it looks nice.
In general, you'd have a bunch of unitaries.
Okay.
So you'd actually have to do all the stuff you did this morning. Yeah. So this is just the dual of the polytope, basically. So all the basis information is stripped away. And we could do the same thing for Alice. Alice, we have a similar constraint down here. It corresponds to a point split. And we have some point merges and some point raises. And we have an upper bound on cheating once we have this. So we're going to look at these two beasts at the same time. And we're going to find a point game. Okay. So the point game, it'll take me 3 slides to get through it, but it's conceptually not too bad. We start with this guy down here, and we're going to do some point splits. So we're exploding the points horizontally. And up here, we're raising these points so that they're vertically aligned with each one down here. Okay? So you can already see this will not be good for optimal weak coin flipping. We're throwing away way too much information. So we've done this. Now what we do is we take these 4 points, and we're going to horizontally point split them this way. And after, we just merge everything until we get a single point. So we had a bunch of points up here and a bunch of points down here. We're just going to merge them vertically like this. And then we're going to take the new points, merge them like this, merge and merge. Okay? And then we end up at a single point right here. So there was two funny things that happened at the beginning with these point splittings, but after it was just a matter of bringing everything together either horizontally or vertically. And why do we care about such a point game? This point game is useful because we have these SDP notions carrying through. So right here, we looked at the dual of Bob cheating towards 1 and Alice cheating towards 0. And this final point, since it was created from a feasible dual solution, it upper bounds the cheating. Okay? And this just comes from weak duality of semi-definite programming. But we also have strong duality of semi-definite programming, which means that you can actually make these tight. Okay? So if you're given the parameters of the point game, you can actually you can move them around in such a way that you actually get this, this value here. So this is an exact characterization of cheating in this sense. But this bounds weak coin flipping only because I've only talked about Bob cheating towards 1 and Alice cheating towards 0. Okay? What we want is a way to use these point games to bound all 4 cheating probabilities. And in general, I don't think this is known. If you have some kind of point game, it only has 2 coordinates, and you can bring it back to a weak coin flipping protocol through a series of steps. But there's no guarantee on what the other 2 cheating probabilities will look like. Here, since we have a one-to-one correspondence between the point games and the protocols, what we can do is we can pair point games. We can look at the point games, and if we see how the splits were done at the beginning, preserve how the splits are done just kind of in a flipped order. You'll get a new point game, and it'll bound the other 2 cheating probabilities as well. Okay? And what's nice here is that these pair of point games, whenever you go back to the protocol, they go back to the exact same protocol. Okay? So the simplified nature of what's happening here allows us to do this, but in general, this is not true. If you take 2 point games, you can't just take them back to the same protocol, as far as I know anyway. Okay? So now we have bounding strong coin flipping as well. Is there a question?
It seems kind of like magic here. You're going to explain more about
So, okay, so the point games and the dual feasible solutions are pretty much in one-to-one correspondence. They look pretty much the exact same. The magic comes in from reducing the SDPs to that specific form. So once you take a complicated SDP and get to something that looks like a linear program, you pretty much get the point games for free. Yeah. Okay, but we can also look at the classical counterpart. You want to ask?
I'm sorry, yeah. So if you're saying that this very simplified SDP is the same as point games, right? That these are the same point games that you kind of also characterize the general SDPs, then shouldn't this kind of say that you don't lose much going from the general SDP to this very simple, almost linear programming thing?
So your question was if you take this simple point game and you turn it back into a protocol?
But you get a restricted class of point games, right?
Yes, this is
you
very
allow fewer
restricted.
rules, I think.
Yeah.
So what's the restriction you do?
Okay, so this morning you took weak coin flipping protocols and you had point games and you had a one-to-one correspondence, or you go from one to the other and back. This, you have a subset of protocols and a subset of point games, and they're in one-to-one correspondence, basically.
You don't have K2K transition.
So this is the only 1 point to many points or many points to 1 point. This is the
Yes, but they have to be done in that particular order that I showed.
What
Oh,
is
I
that
see.
particular order?
So there's point splitting, and then there's splitting this way, and then just merging like this.
I see. So 2 splits and then boom, 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 boom.
Yeah, yeah,
And you're
exactly.
allowed to merge for how many rounds you want?
Well, the merging takes place just like this. So
Like
there's
many
actually,
mergers or many mergers?
so there's actually, you have to merge so many points each round. So you have to merge certain indices, and then you have to merge certain ones, like this.
But will
I
that
have-
process always terminate after only 3 mergers, or can it in general take more?
It'll always converge. Yeah. So you're always taking 2 to the n points to 2 to the n minus 1 points. And sometimes you have to raise them such that they're aligned so that you can merge. But yeah.
So I guess the number of merges corresponds to the number of register flips? Or?
The number of merges corresponds to the number of dual SDP constraints. And that corresponds to the dimension of the messages that has been revealed up to a certain point in the protocol.
Which is the register.
Yeah. And we can also look at classical point games. So I said that this reduces to something that looks like almost an LP. So I looked at that a little bit and was wondering what this polytope was actually characterizing. And it's characterizing cheating in a classical protocol. Okay? And this classical protocol is very similar to the quantum protocol, except instead of superposition, you're just using probabilities. Okay? Instead of creating this weighted superposition, you're just sampling probabilistically. Okay? So basically, you're removing this quantum measurement, which makes the quantum protocol secure. And we can look at the dual LPs. And we can also find a classical point game, okay, which is a special case of the quantum point game. Okay? And basically, what we're just doing is removing the point splitting at the beginning. All we're allowed to do is raises and merges. Okay? So here's a classical point game that favors cheating Alice. Okay? Assume this is an optimal point game, so this is the optimal final point. Then we're saying here that Bob can only cheat with so much probability, and Alice can cheat towards 1. And over here as well, this is one favoring cheating Bob. Bob can cheat towards 1, and Alice can only cheat with so much probability. So classical protocols are nice. They made this nice picture. But we can actually study the quantum security using the classical protocols. Okay. The first thing is that we have a classical equivalence as well between the classical protocols and the classical point games. And what we can show is that classical point games have large final points. There's no way for a classical point game to have a final point that's strictly within this box here. And because of this weak duality, strong duality stuff, this shows that classical coin flipping protocols are insecure.
Then can you explain why it doesn't go to half? I mean, because we have classical protocols, right, where one of the players cannot cheat at all and the other player cheats perfectly, right? So
Yes, this is a good question. So there's actually some kind of magic that's happening in here with how they're raised. So I said the merges have to take place in a certain order. So there's some, over here, there's some, you're only merging some points at a time. And then sometimes you have to raise them because you have these point races.
So you mean that the restriction you put on classical protocols don't allow to go to half?
The restriction on the point games. The actual recipe of the point games, you have to follow a particular recipe. Yeah.
Does this give anything new for the classical games?
We already knew classical games were insecure.
Yeah, but is this just another way, or is there some additional information that you got?
Yes, there actually is some. So I'll get to your thing in 30 seconds. So we can show that classical coin flipping protocols are insecure. So this is another proof for this class. But by looking at the classical security, we can show that at most one party can cheat perfectly. Okay? And since classical is an upper bound on the quantum is the stronger one, this holds in the quantum case as well.
What do you mean by at most one party can cheat?
If Alice can cheat perfectly to determine the outcome, Bob cannot.
Even if the protocol is like totally stupid.
Yes.
Ah.
Yeah. So it's a bit of a safeguard. Even if you choose these protocols in a really stupid way, they both can't cheat perfectly. And more surprisingly, if you look at Kitaev's lower bound in this setting, and you try to saturate all the constraints, so you want a protocol with cheating exactly 1 over root 2, you can show that if a quantum protocol has this property, then the cheating in the quantum case equals the cheating in the classical case.
For which property?
So you have all 4 of the cheating probabilities equal to 1 over root 2.
Okay.
So basically, if you have a protocol where Kitaev's bound saturated, the product equals 1/2, you can show that these 2 probabilities are also attained in the classical version of that protocol. And therefore, one of them has to equal 1, one has to equal 1/2. Do you have a question?
Yeah, I'm confused about the fact that you can't both cheat. For example, if I have a protocol where,
Mm-hmm.
Alice picks a random bit, sends it to Bob, and Bob is supposed to send back the same bit to Alice, and what Bob sends back to Alice is then taken as the final outcome.
And what Bob sends back to Alice?
Yeah, so Alice picks the random bit, sends it to Bob. Bob is supposed to send it back, and Alice doesn't check whether she's getting the right one back.
So Bob's generating a completely new random bit?
Not honest Bob. Honest Bob sends bit back.
But cheating Bob could.
Cheating, yeah. So cheating Bob could fix the bit to what he wants.
Yeah, so Bob can cheat with probability 1.
Cheating Alice could also fix what she sends in the beginning, and honest Bob sends it back. So they can both cheat with probability 1.
The cheating is the probability that the honest player accepts the outcome of the dishonest player. I can always say 0, you can always say 1. So
yes, but in this case, both will. If only one cheats, they will both agree, but everyone can cheat.
No,
with probability 1.
Alice will not agree. If I send you 0 and you're
of course
supposed
you
to
will.
send me
That's
0
my
and you
protocol
send me 1,
description.
I'll say
That's
sorry.
my protocol description. Alice will agree. I mean, it's a stupid protocol, but I mean that there are some protocols where only one can cheat. That's clear. But so
there could be protocols where they both could cheat perfectly.
Sorry?
I'm not ruling out the possibility that there exist protocols where they can both cheat perfectly.
So what do you rule out?
I'm just saying in this class of protocols,
in this class.
either quantum or classical, that's not the case. Okay, so here's some open questions. So I want to find the optimal protocols within this family. I still haven't been able to do it. I've been looking at the SDPs, but they've been quite difficult. And we've done some numerical tests showing that 3/4 is optimal. We've checked 4 and 6 round protocols with large dimension messages. We actually checked about 10 to the 16 protocols.
Which protocol did you actually find? I mean, what's the number that you actually achieved?
3/4 is the best. Oh, sorry, I forgot to mention the 3/4 protocol of a minus is within this class.
Okay.
So we know of a protocol of 3/4, and we want to know if we can do better. So we think 3/4 is better, and we can use this equivalence to point games to prove it if we better understand what's going on. Can we use time-independent point games to simplify things? I'm not quite sure. I don't think so, but maybe. And in general, can we find point games for strong point flipping? Okay. Can we kind of take 2 point games and map them back to the same protocol, or some other kind of magical business? And ultimately, what are the optimal solutions to the SDPs, which characterize optimal cheating use in the protocol? Thank you.
We already know that you can take weak coin flipping protocol of bias epsilon and to turn it into an optimal strong coin flipping protocol, the square root of square root of 2 plus epsilon.
Mm-hmm.
Suppose you take an optimal strong coin flipping protocol with bias in.
Mm-hmm.
Can you use it as a black box to create a weak coin flipping protocol with bias smaller than P?
So the question is, can you go from strong coin flipping back to weak coin flipping?
But with a better parameter.
As far as I know, no. If we can find an improvement in strong coin flipping, it may give us some insight, but I don't think this would automatically reduce to something better.
I think that the answer is no, but I'm interested in whether you have proof or I don't know, insights for why you think the answer is no.
So when I was starting this, I wanted to find a better strong coin flipping protocol, something that was in between 1/2 to 3/4, to get some intuition behind what to do, how to find better weak coin flipping. So right now, the best weak coin flipping has cheating 2/3, the best simple explicit protocol. But yeah, I don't have any general idea on how to do this.
Okay, I think we should move on. So let's thank